value. So as you can see on our bottom right corner, we have our predicted output 1, 0, 1, 1, 1, 1, 0, 0. Our true is 1, 0, 1, 1, 1, 1, 0, 0. And as you can see, our error value has decreased by far as it progressed. So this is my second neural network. So I actually coded 2 different versions. So when I was coding it, I didn't want to forget the code. So then I built one version with like a lot of nodes. So then I know what each line of code did, but that got like a little too messy. So then I coded a second version with only the necessary nodes. We'll play this. So right now it's training. I'm training the network. And these are the weights after the training, and then our real output and our predicted output. So that's how our basic recurrent network works. So this is an image of a recurrent neural network unfolded into multiple perceptrons, which for previous time steps. And then, as I already said, they're used for sequential data. And the thing with them is recurrent neural networks is that their weights are actually shared. So then this adds like a recurrence loop in the hidden layer, which allows it to access previous inputs and outputs and weights. Also, the recurrent neural network doesn't assume that the inputs are a fixed length and they're independent. Because, for example, if the inputs weren't independent of each other, the recurrent neural network would just completely crash. So then steps. So first, we have to our normal equation, we add the previous weight of the previous time step, multiplied by our previous inputs, and then we sum it up, and then we add it to the current neuron information. And then for the current neuron, we multiply by the next weight, and then that would be our output for our output cell. And then for back propagation, for recurrent neural networks, we use something called BTT, which is back propagation through time. And for those of you who don't know, back propagation through time is when you adjust all the weights, so the weights of the previous time step as well. So then here's an example. So then let's just say we have a sentence, like a girl walked into the bar, she asked the bartender, can I have a drink? And then the bartender says, certainly. What would she say at the end? So then if we ask the recurrent neural network to predict what would she say, the recurrent neural network would have like previous weights. So then it would look at a girl walking to the bar, and then what do you normally call a girl? It would be either man or some other name. So the recurrent neural network would use something called a softmax regression function, which computes probabilities of what word it might be. And it would compute the highest probability for the word man. So then the recurrent neural network would output the word man. But the problem with normal RNNs is that there's a problem called the vanishing gradient problem. And this problem occurs with a lot of inputs. So if you have like a whole, like 2 whole pages of, let's just say, Shakespeare books, and if you input it into the recurrent neural network and ask it to predict the next sentence, it would just completely crash. Because as you back propagate the gradient gets smaller and smaller, and suddenly it just vanishes. And then now we can't back propagate. So then our recurrent neural network just crashes. Also, this is also called the exploding gradient problem if the gradient gets too large, but this almost never happens. So is there a solution to this? And the answer I found was yes, and that solution is LSTMs, also known as long short-term memory networks. So the long short-term memory network is a type of recurrent neural network that was designed to deal with the vanishing gradient problem. There are three main components of this. There's the input gate, the internal state / the forget gate, and the output gate. So first, let's look at the input gate. So the input gate, it has 2 inputs. So the current input and the previous cell output. So first, it uses a type of activation function called a hyperbolic tangent, also known as tangent function, which squashes our inputs between 1 and -1. So on the bottom right corner, that's the equation for our squashed inputs. So this gets it ready for the next stage. That stage is multiplying the squashed inputs by another activation function called the sigmoid function. And this squashes our squashed inputs between 0 and 1. So then after it does this, it determines which inputs should be switched on or off. So if the inputs are closer to 0, it switches them off. And if it's closer to 1, then it keeps them on and propagates them into the hidden layer next. And the equations down below right express the equations for the input gate. The second step is the internal state and the forget gate. And this, in my opinion, has a lot of magic. And this is where like the most happens. In this, our inner state at the previous time step is added to our input gate equation. And what this essentially does is that it learns the relationship between the inputs, so like the previous cell output and the current input. And then what the forget gate does is that it applies another sigmoid activation function, because essentially we want to get rid of unnecessary data. So then again, if they're closer to 0, they're forgotten, and if they're closer to 1, they're remembered. And our output for the forget gate can be expressed as the one on the right. And then this is also a factor of reducing the vanishing gradient problem, because notice how I said added and not I didn't mix. We didn't mix the internal state with the input gate equation. We just added it, and that helps reduce the vanishing gradient problem. And the last step of the LSTM is the output gate. What the output gate does is that it has 2 components. Again, we have our tangent function, which squashes and prepares our data between -1 and 1. Second is that we have another sigmoid activated nodes, which squash our outputs between 0 and 1, and it determines which outputs should be outputted. So then if it's closer to 1, it outputs them. And if it's closer to 0, it just completely forgets them. And that equation can be expressed as bottom right. So in total, our final equation for our LSTM is this. So I know what I just said is a lot to take in, and it can be confusing at first, so I created an analogy to help you. So you can think of it as 3 networks inside a network, inside a network. So I went over to the LSTM, but I really didn't say like how it reduces the vanishing gradient problem at all. So to summarize, it reduces the problem by adding new weights, new weight matrices, and the new equations instead of mixing them and multiplying them. Because if we mix them and multiply them, they either get too large or they start to gradually decrease as we then propagate them through each time step. And then adding our dependencies rather than mixing them, it adds a sort of a recurrence loop and keeps our computed gradient between 0 and 1, which is what we want, to keep our LSTM to compute information between between 0 and 1, so then it knows what to forget and what to output. And then the forget gate also helps by clearing away any unnecessary data. So then LSTMs and RNNs, they can be used for speech translation, log analysis, and text summarizers. But personally, I'm actually interested in integrating recurrent neural networks and long short-term memory networks into a blockchain, so then it can actually figure out where hashing power and where hashing functions can be used more effectively. Because I did some research, and hashing power up to now, it hasn't been used that effectively, and lots of it is going to waste. So I came up with this idea when I was at the blockchain economic event, which I'm sure many of you were also there. And then I actually confided my idea with the CEO of Epic Blockchain Technologies, which is a blockchain startup based in Toronto. And I'm actually currently scheduling meetings with them to discuss how I can take this idea further. So I want to end off by saying that neural networks and deep learning, many people get the wrong idea, is that they will take over jobs. They will surpass human intelligence. But the fact is, we control AI. We control artificial intelligence. AI, neural networks, and deep learning, they will create new jobs, new opportunities, but they will create new jobs, and thus creating a better economy. Thank you.